All right, hey y'all, we're going to be talking about reaction rates. Before we get started, I want to start with a little picture. Give us an idea of what happens. So reactions occurring aren't this weird, unknown thing. Essentially, they're just like blobs that when they collide, they stick together if they react, and if they don't, then they don't stick together. So you can imagine if you've got like some A plus B forming, like, let's say AB, and let's say I have a jar and I have some A's and B's in there. So essentially, every time in this jar, things are moving around, right? Because they're always moving. Electrons are always moving things around. But every time A hits B, it forms. Now we have an AB. I'll just kind of like put it together like that. And then the rest are still the same. Until they collide with each other, they're going to remain that way. But when they collide with each other, boom, they form an AB. So reactions occur as a result of collisions. So if we increase how quickly these collisions can occur, we can increase the rate of the reaction. Rate is kind of a similar concept to speed. So for example, if you're driving, let's say you drive 20 miles per hour, that's the rate at which you drive. In 20 miles, driving 20 miles will take you an hour. If you got an hour, you can drive 20 miles. So that's just another form of rate. So it's essentially how fast something can occur. So let's talk about the things that can affect the rate. If we can increase the number of collisions, in other words, if you can get A and B to smack each other a lot more, you're going to have a faster rate or a higher rate of the reaction. So there's several different things we can do. The first is concentration. So oftentimes, if you, instead of just having A and B kind of spread apart, if you add more of them, they're more likely to collide, and therefore you're going to have more of this AB compound, whatever it is. So concentration has an effect on the rate. Temperature. So if we increase the temperature, and this happens in two ways. One is that if you have, say, a molecule that's bonded and you need to break it, in order to break a bond, it takes energy. It requires energy. I'm going to write takes just because it's smaller and it'll fit there. But breaking a bond takes energy. The second thing is temperature is reflective of this kinetic energy. In fact, temperature is a movement of the kinetic energy of the molecules of something. Let's talk about what kinetic energy is. Kinetic energy, we normally see it as, if you've ever taken physics, is 1/2 mv squared. It's the mass of something times its velocity squared, where velocity is the speed of something. All right, so let's say you have these A and B at a low temperature. That means they're barely moving. Boom, boom, boom. So let's just draw little arrows like to indicate, I don't know why, but for some reason I picture like Pong, like doom, doom. If you've ever played Pong, probably not. You probably don't know what an Atari is. Okay, but if you do, let me know and I'll give you a high five. Okay, so here we have things at low kinetic energy. In other words, a low temp. They're moving very slowly. And much like you, when you get warmed up, like let's say you're stretching in order to go for a run, or you run the first 5 minutes or something like that, your body warms up and suddenly it's moving better. So when you have a higher kinetic energy, these things are going super fast. And all of a sudden you have Pong on roids. you of course need the sound effects, and they're bouncing all over the place. And if they go really fast, the chances of them hitting each other is much higher. So you'll have more collision. So at high kinetic energy, in other words, high temp, you will also have more kinetic energy. Okay. Structure and orientation of the colliding particles. So where these molecules hit is kind of important. So let's say you've got in a container, you've got the AA, and you're trying to react them with some B. Well, the B can hit this A and become AB. So it can come in and go boom and mesh with this A, or it could come on this side, boom, and hit that A and still become AB. It doesn't really matter because remember, these are three-dimensional molecules. So if it happens to hit on this side, it's BA, but just flip it around, it's still AB. As opposed to this, where you have AX. So if B hits the X, it's not going to react. B has to hit the A in order for it to form AB. So the B has to go over here. Here, the B could have gone there, or it could have gone there, and we would have gotten here. It doesn't. So this reaction will be faster, and this one will be slower, simply because of the chances of the particles interacting and hitting each other at the right spot. So, so those are the three main things that we would talk about in terms of what increases the rate of the reaction. Again, the number one determining factor is how many times is it going to collide. And if we can enhance the number of times something is going to collide, we can affect the rate, we can enhance the rate. All right, so let's talk about defining and measuring rate of reactions. So how do we actually know what a rate of reaction is, and how do we measure it? Well, there are many different ways. Before we get there, it kind of helps to talk about the equations that we'll be using, and hopefully they make sense. Just like our little miles per hour here was a change in distance divided by a change in time. We don't really think about it that much, but it's really that simple. It's the amount of distance we go over a certain amount of time. A rate is the same thing. It's the change in concentration over the change in time. How much stuff there was over how much time it took for that stuff to disappear or grow, or whichever we're looking at. For the reactant side, anytime we're looking at the rate of reaction for any one of these, it's always going to be negative, and that's because the rate's going to be decreasing. Let's talk about why that is. Every time something like A and B collide, you no longer have an A or B. The concentration of A goes down, the concentration of B goes down, but the concentration of AB goes up. So if you're here, these concentrations are going to go down over time. Well, that concentration goes up as the reaction occurs, and I hope that makes some sense. Okay, so the rate is equal to the negative change of the reactant divided by the change in the time. And if these reactants have coefficients, we'll talk about how that affects it here in the next page, I believe. Okay, so we don't have to specifically look at one reactant. We looked at H2, but you could also look at I2 and HI, and you'll get the same answer. So we looked at H2 and we said, okay, the change in H2 over the change in time, and we took the inverse of that, or the negative of that, excuse me. For the I2, we did the exact same thing. It would be the negative change of I2 over the change in time. Or if we looked at the reactant side, remember this is, or the product side, remember that's the side that's going up, and there's a coefficient of 2. So we have to take that into account here. And that's why we have the 1/2. If it had been a coefficient of 3, we would have had a 1/3 here, or 4, we would have had a 1/4. All right, and so essentially the rate is equal to 1/2 the amount of time that HI is going up over time. And notice that it's positive because now we're talking about the product side. So we're gaining product, so we don't need to negate that negative anymore. Okay. So, yeah, and then again, the half is because for every 2 moles of HI, there's only 1 mole of H2 and I2. Again, the reaction was H2 plus I2 yields 2 HI. So for every 2 moles of this, we lost 1 mole of that and 1 mole of that. And that's why we have to take into account the half. All right, again, the rate for all of these should be exactly the same because we're talking about the rate of the reaction. We're just talking about using different products or reactants in order to figure it out. All right, this graph looks like, if you're anything like me, but let's take a second and take a breath and look through it. Okay, here we have H2, and this is still regarding this reaction up here. We know that H2 has to go down. As H2 goes down, what's going to happen to the HI? It's got to go up, right? It's got to go exactly up, and at a rate that's going to be double, or a concentration that's going to be double this one going down, because for every one of these that we lose, we gain 2 of those. So that's why this slope is bigger. If we flipped them over, it'd be 2 times the amount of this one. Okay, there are 2 different kinds of reactions we're going to talk about, or rates. We're going to talk about the average and the instantaneous. All right, the average rate is just the rate over any given period of time. So again, remember, rate is change in concentration divided by change in time. So you could choose any period of time you want, or any concentration. Let's say you want to know the average between here and here. Then you would use the time difference here, and looking at the concentration from about 0.5 down to about 0.1. And that's how you would find the average rate. We'll do a calculation example here in a minute. And we can calculate this again for any time period. So this is the average of the rates within a specific time period. It would have been the slope of the line. So here they took an average of the rates at as H2 changed from 1 to 0.819. And it said, hey, when it did that, its rate was 0.0181 mole per liter per second. There. You can see, like, let's say at 50,000, they took one between 50 and 60,000 ish right here, and they said that that's 0.0067. So they took several different average rates depending on the time. One thing to note is, see how the rate went down? Why does the reaction slow down as it progresses? We should stop and think about that for a second. So let's go back to our AB. So every time an A reacts with a B, forms an AB, that can no longer react, that's gone. And then this one forms with that one, that can no longer react. And that one forms with that one, that can no longer react. So when there's a bunch of them, there's a lot that can collide, and you can form this stuff pretty quickly. But over time, you can see that there's fewer and fewer of them to collide. And that's why when there's fewer and fewer of them to collide, they don't collide as often, and the rate goes down. So that's why your rate starts at 0.018 here and ends all the way down at 0.003 after a long period of time. The instantaneous rate is, you're going to have a tangent line. It's the rate at a particular point in time. So for an example, here, they said, using H2, find the instantaneous rate at 50 seconds. Okay, so let's go look at 50 seconds. At 50 seconds, and it said for H2, so we're looking at this one right here. At 50 seconds, we're right here. It drew a tangential line for you, and it calculated the change in y over change in x, which is how you find the slope of a line, right? Slope always equals change in y over change in x. Rise over run, as some people will say it. So that's it said that at this particular point in time, the change in y was this 0.28, negative 0.28, and the change in x was this 40 seconds. And so I calculated it for you. It said, okay, 0.28 over 40 seconds gives us this 0.007. Now, if I asked you for the instantaneous rate at 50 seconds for delta HI, even though this is the product, just to remind you, this was the product going up, we should still expect it to be exactly the same. And in fact, it is. So that 50 seconds, they drew a tangential line here. The time is still 40 seconds, but the change in the change here is going to be 0.56. It should be double that one, just to refresh your memory. And sure enough, when you do that calculation, you also get 0.56 divided by 40 times that 1/2 gives us 0.007. We're doing the half again because, again, we're talking about HI, and we defined that rate a little earlier. Note these rates are the same. I think this is the 4th time I've mentioned it, so keep in mind that's a very easy test question I might ask you to ensure that you understand that the rate for any product or any reactant at any given time has to be the same. All right, moving on. Okay, let's look at this balanced equation. Okay. So it says in the first 10 seconds of a reaction, the concentration of I- drops from 1 to 0.86. That looks to me like that's going to be about my change in I-. And this is telling me that's my change in time. So it went from here to here in 10 seconds. And we want to calculate this average rate of reaction over that given period of time. Well, for A here, let's see if maybe I can keep it all in one side. We'll see. For A, it wants to know the rate of this reaction. We could have used any of these things, but because we could have used H2O2, H+, the I3 negative, or the water, but because, well, really we couldn't use the water. You can use these aqueous things. But because it tells us the I- concentration, I'm going to assume that we're talking about this I- right here. Rate for this I-, see how it's got a 3? Would equal 1 over 3. It's a reactant, so I'm going to give it a negative sign. Negative 1 over 3 times its change in concentration divided by its change in time. That's how we find any rate. And if you need to, pause it, go back, look at the other rates. We're always taking the change in concentration over change in time. And then if it's got a coefficient, we go ahead and throw it right there. All right. Well, if we go ahead and plug some of these numbers in, anytime we have a delta, it's always delta equals final minus initial. Always. So our delta I- equals our final concentration. So it started at 1, it dropped to 0.68868 minus 1.000 specifically. That is our change in concentration. So what is that? 0.132. I'm doing it in my head. Negative 0.132. I hope. Mole per liter. So here, when we go to do our delta I, we know that that's negative 0. Actually, let me write the whole thing out. We had negative 1 over 3 times the change in I-, all over the change in time. Our delta T, well, we ended at 10 seconds, and we began, we're assuming, at 0 seconds, unless otherwise stated. This should be 10.0 seconds. So if we calculate this out, let me go ahead and grab my calculator, just to make sure that I get the same answer as I got before. I'm going to do 1 divided by 3 times, and I'll start in parentheses, 0.132 divided by 10. I know that those negative signs are going to cancel each other out. You have a negative times negative is always a positive. So I get positive 0.0044 mole per liter per second, big M per S. Okay, so this is going to be our rate at that time interval. B says determine the change in the concentration of H+. That is, it wants to know the H+ over delta T during that time interval. Okay, well, if we were doing it for the H plus, we look to see if it's got a coefficient. We look to see which side of the equation it's on. It does have a coefficient, it's 2, and it's a reactant, so I'm looking at -1/2 delta H, the change in concentration of this H plus, over the change in time. And it happens to be that that's what we're solving for, this whole quotient. So this is going to be like our x. So in fact, if I replace this whole thing with x, that might help even more. So our rate equals -1/2 times some x. We're solving for x. Do we know our rate though? We sure do, because it said it was during this same time interval, during this time interval. In other words, it has to be the same as what happened to A. Whatever happened to this had to happen to that. It has to be the exact same rate. So our rate is 0.0044 big M per second. And now we just plug and chug. So if I move this whole equation over here and set it up, I have 0.0044 mole per liter per second equals -1/2 times my x. In order to solve for x, you're just going to multiply each side by 2. So I get 0.0088 mole per liter per second equals x, specifically -0.0088. And if you remember, x was that change in H plus over change in time. That would be your answer. Alrighty. So now let's talk about the rate law and the effect of concentration on rates. Okay, so sometimes, let me get another piece of paper for this AB thing. So you might have let's say 3 different containers. There are 3 different types of rate orders we're going to talk about, and there are more than that, but we're going to talk about a 0 order, a first order, and a second order. All right. Let's say you have, stick with A's and B's, some A. All of these have the same amount of A. Okay. Now let's say you add some B here. And you want them to react. In a 0 order reaction, adding B doesn't speed up the reaction. It's just the same as it would have been before. No change in rate. But here, if we add B, I probably should have done a better job starting with this. In fact, I'm going to add some B there. Okay, I'm going to take a step back. So let's say we already had 2 B's here, and I doubled the amount of B's. I added 2 more. There was no change in the reaction. Here I have 2 B's already, and I'm going to add 2 more. I'm going to double it, and the change in the reaction is going to be that I doubled the concentration. I'm going to double the rate. This is going to go pretty fast. Here, I doubled the concentration. The rate still kept going along like a game of Pong. Here, I doubled the concentration. They move faster. Here, in a second order, if you double the concentration, you quadruple the time the reaction happens. So here I have two B's. I'm going to add another B and another B. Super fast. It's going to go 4 times the rate just by doubling the concentration. Different reactants have different effects on the rate. It depends on the actual reaction, and it depends on something that we'll eventually learn is K, which is the rate constant. So I just kind of want to show you the general difference. A 0 order, if you add more stuff, doesn't change how fast the reaction happens. A first order, if you add more stuff, if you double it, it's going to double the rate. If you triple it, it will triple the rate. And a second order, if you double it, it quadruples the rate. It's always going to be exponential. So if you triple it, it's going to go 9 times the rate. So 3 squared, in other words. But we'll talk about the math here in a bit. It goes way faster. Cool? All right. So K is called is like something of proportionality. It's specific to each reaction. We're going to go ahead and call it the rate constant. And N is the reaction order. So where N was 0, in a 0 order, we would set N equals 0. First order, N equals 1. Second order, N equals 2. Oh, look, I got it written there for you. And some pretty pictures as well. Okay. So again, if N equals 0, the rate order is 0. If N equals 1, it's a first order. If N equals 2, it's a second order. So this, you can look at this and kind of get an idea of how second order is going to run out of concentration faster, and it takes longer as you get lower in concentration. This one's relatively consistent all the way down, with the 0 order, and the first order somewhere in between. But I like this one a lot because it talks specifically about rate. All right, so this is A. So let's say we have some kind of thing that is A going to products. In a 0 order reaction, if we add more A, nothing happens to the rate. It doesn't go faster at all. Okay, nothing's going to happen. In a first order, which is this straight line right here, as we add more A, the rate goes up proportionally. So 0.2 to 0.2, 0.4 to 0.4 is just going to go up perfectly. Okay, so it's going to get, if you had a whole bunch of A, if you wanted to make it go fast, you're going to go, your rate order is going to go faster. Or your, excuse me, rate. Your reaction will go faster. I can do it. As opposed to second order. Notice here, when we add a little bit of stuff, the rate goes up quite a bit. A little more stuff, the rate goes up a lot. A little more stuff, the rate goes up even more. It's not this steady little thing that would have gone like this. It's exponential, and it goes up and doubles, or it's to the square of the amount of concentration that you put in there. So if you get 0.2, it's going to go up by 0.4. If you do 0.4, it's going to go up by 0.4 squared, which is 1.6. Here's another way to look at it. In 0 order reactions, this is how we write them. Rate is equal to K, the rate constant, times A, which is the concentration of something, to the 0 power. Remember, anything to the 0 power is 1. So if you have 25 to the 0 power, or 372 to the 0 power, or x to the 0 power, it doesn't matter. All these things equal 1. So this equals 1. In other words, rate simply equals the rate constant. I love these tables. I hope you find that you love them as well, because to me, I can tell a lot about a reaction just looking at this. And it's a lot of repetition of what we've already said, but let's take a look at it. Here, A went from 0.1 to 0.2. Hopefully you agreed that from here to here, it doubled. What happened to the rate? It still stayed at 0.015, it didn't change. And that, by definition, is a 0 order reaction. If you increase the amount of A in there, or double the amount of A, and it didn't change at all, this is definitely 0 order. The units of K would be big M per second. Again, your rate is always going to be big M per second, and units of K are going to change depending on which order it is. So I wrote these in here just so you can kind of get used to seeing them. So in a zero order reaction, the units of K are big M per second. So if we solved for K, it would be big M per second. Let's look at a first order reaction. Remember, that's when it's directly proportional to the contents, or the concentration, also the contents, the amount of stuff that you add. In that case, rate equals Ka to the 1. So here, check it out. Hopefully you agree, we doubled that. When we doubled that, what happened to this? It went from 0.015 to 0.03. It also doubled. That is by definition also a first order reaction. Or here, where we went from 0.1 to 0.4, we quadrupled it. The concentration also quadrupled. The units of this are going to be in inverse seconds. And that's because if we rewrite this, rate equals Ka to the 1. Remember, we always need this to be in big M per second. And this has to be in big M. So the only way we're going to get units of big M per second is if this has units of inverse seconds. In other words, big M over second equals something times big M. This something has to be 1 over S in order to have moles per second, or mole per liter per second, and mole per liter per second. It's the only way to do it. All right, in a second order reaction, remember, this is where we're moving things really fast. We doubled something and it quadrupled, and that's exactly what you'll see here. As we doubled the amount of A, we went from 0.1 to 0.2. Our time went up 4 times. When we quadrupled it from 0.1 to 0.4, this went up 16 times. So this was times 4. This went up times 16. It went super duper fast. Cool. So you can make a reaction go really fast if it's a second order reaction. Its units are inverse mole per inverse second for the exact same reason we talked about here. It's the only way to get the units to cancel and be left with big M per second. Okay, so using these charts is super helpful, I think. Far more helpful than what we're about to do, but what we're about to do is necessary evil. And I'll show you what I mean. Okay, so let's say you need to find the rate. So I'm going to leave this here. It says, let's look at the second order chart above and see if we can determine the rate order, pretending we don't know it. So as easy as it is to say this doubled and this quadrupled, therefore it's a second order rate, let's pretend we couldn't figure that out. Let's pretend that data wasn't very clear or we didn't quite understand, and you will come across those situations. This is where we have to use this problem, where we take, essentially you just look at the ratios of 2 different rate equations. So we know that any rate equation is rate equals K times the concentration of the thing that you're looking at to the n, where this is the rate order. And what you can do is you can set these 2 things on top of each other, one of them and then another one, and you can solve. So bear with me here. I'm going to walk you through some stuff, and it might have been a while since you've seen logs, so just bear with me. All right, the 2 things I'm going to look at are these 2, but you could have chosen any 2 points, I'm going to call this one my rate 1 and this one my rate 2. Really, this is the rate 1 and that's the rate 2. I'm going to use this equation here, but I'm going to put it up here so we have some room. Our rate 2 was 0.24. I'll just rewrite it, I guess, because I already started. So we're going to take our rate 2 times K, concentration of A at some second point in time over N, over K, A, some first point in time over N. Okay. Our rate 2, again, was 0.24. our rate 1 was 0.060. What goes with 2 was the Ka2. So at our second rate, where it's 2.4, the A was 0.4. So I do K times 0.40 to the power of some n over K. Now I'm at this first rate, which is the 0.6, and the concentration is 0.20 to some n. All right, so this is the equation that we're looking at, and we're trying to solve for these n's. They got to be the same because they're both n. All right, step number 1, k's cancel. You have something divided by itself, it's always going to be 1, so that cancels. That's good news, right? Next, you can do this. 240 divided by 60, you know, is 4. In other words, 0.240 divided by 0.060 is 4. So this equals 4. So to rewrite right now, we have 4 equals 0.40 to the n over 0.20 to the n. Much simplified, right? Now let's keep going. You can actually combine these two. In other words, 0.40 over 0.20 to the n. And now we have 4 equals that. And even one further, you know 0.4 divided by 0.2 is 2. So that's 2 to the n. So right now we have 4 equals 2 to the n. And we need to solve for n. To solve for an exponent like this, you have to take the base 10 log of both sides. So log of 4 equals the log of 2 to the n. And I don't know if you remember this, but when you take a log of 2 to the n or log of something to the exponent, that exponent goes out in front. And really now it becomes n log of 2. So our log of 4 equals n log of 2. Now remember, we're solving for n. We want to get n alone. We're going to divide both sides by log of 2. So essentially we have log of 4. That was meant to be like a big old arrow. Log of 4 over log of 2 equals n. And if you plug that into your calculator, you find that it is a perfect, beautiful 2. All right. Ooh, darn. Thought I was done. I was excited. I'm not. Suckers. Means you're not either. I'm sorry. Let's keep going. Last but not least, we have rate orders for when we have multiple reactants. So in this case, in the previous cases, we were only looking at like a reactant that was just A. Now we have A and B because A plus B forms some C plus D. And then the rate orders are not going to be the same for each reactant. This one is N, like we just solved for, but this one's M. So we just don't know what the rate order is going to be. But it's kind of cool. We can look at this and solve for it in the exact same way we solved for the other one. Look to see what doubled, and then find to see what happened to the rate of the reaction. So, for the first one, let's go ahead and look at NO2 to find the rate law for the reaction. So the rate law for the reaction in this case is going to be rate is going to be K times NO2 to some M times CO to some N. We don't know what that M and N are, but let's use the table to try to figure it out. Okay, let's look for NO2 first. In order to look at NO2, what you want to look for is a situation where CO had no effect on the reaction, but NO2 may be doubled. In other words, look for where CO was the same between two trials and where NO2 doubled. And I see that happened right here. I see that CO was 0.1 in 0.1, But during that time, NO2 doubled. So NO2, in other words, NO2 is the only contributing factor to the rate. It's the only thing that would have affected it. And I see immediately that it went from 0.002 to 0.008. So when this doubled, what happened to this one? It quadrupled. What kind of order does that make it then? That makes it a second order reaction, meaning this has to be 2. So when this doubled, this one went up by 4. So again, it's important that you don't look at two, like if I looked at this one and this one where 2 things changed, we wouldn't have been able to tell anything. So always make sure you're looking for where one of the reactants stayed consistent and the other one changed. All right, now let's look at CO. CO here, I'm looking for where NO2 stayed the same, but CO doubled, and I see that from here to here. Here, NO2 was 0.2, both runs, but here, the CO doubled. And if the CO doubled, what happened to the rate? Ah, it stayed the same. So if the CO doubled, but the rate didn't change by anything, it stayed by 1, that would make this a 0 order. It didn't change at all, and therefore that's going to be a 0 order. So our rate law here is K NO2 to the M, or excuse me, NO2 squared, I can do it, times CO to the 0. And that's going to be our rate for this reaction. So that solved A. It said write the rate law for the reaction. That's that. B wants to know the rate constant for the reaction K. Well, to do that, now that we have our rate law, we can use any of the numbers from this chart, plug them in for any particular experiment number, and solve for K. All right, so let's do that. Again, we know that rate equals K times NO2 squared times CO to the 0. Remember, anything to the 0 is just 1. So really our rate just equals K NO2 squared. You can choose any line you want, any line at all that you want to do. I'm going to go ahead and look at the first one just because it's right there. So the first one, my rate was 0.0021 was my rate. This is what we're looking for. And in that first trial also, our NO2 was 0.10 mole per liter. So my rate was 0.20, or 0.0021. I'm setting that equal to K, which is my unknown, times my NO2 concentration, which is 0.10, and then I've got to square it. If I square this and take my 0.0021 and divide it by that 0.1 squared, I find out that K equals 0.21. My next question to you would be, what would the units be of this K? Well, you can go back to previous pages, or maybe you even memorized it, that in a second order reaction, it's m to the negative 1, s to the negative 1. And that would be our answer for B. Is that it? I think that's it. Word! All right, guys, have a great day. I'll see you in class. Bye.